Hello, my name is Advay Singh and I'm an undergraduate at the University of Michigan. Today I will be presenting Gigaflow, pipeline-aware sub-traversal caching for modern SmartNICs. Virtual switches are a key component of the data center network that allows sophisticated packet processing at the end host and enable connectivity between virtual endpoints like VMs and containers. They support multi-table packet processing pipelines comprising of dozens of tables that implement an ordered set of networking policies. Some of these policies require recursive application of rules where the output of one rule becomes the input of another and possibly even the same type of rule. Similarly, when packets are encapsulated or decapsulated, they need to be processed again because they effectively become new packets with different headers. Therefore, vSwitch packet processing pipelines support arbitrary control flows through these tables, including resubmission. Packet processing begins at the first table in the vSwitch pipeline, where it is matched against priority sorted rules. These rules can match on arbitrary header fields, and the highest priority rule is selected. In this case, the rule is matching on the Ethernet address, the destination Ethernet address. Its actions modify the packet, and if necessary, another lookup is invoked in a different table by resubmission. This process continues, where one after another, table lookups are performed, and if matching rules determine that more processing is needed, they keep submitting the packet to the next table written in their actions. This unique sequence of table lookups through the vSwitch pipeline for a given packet is called a traversal. A vSwitch generates such traversals through its packet processing pipeline, which are then mapped onto the underlying hardware architecture. At the time of their inception, the target architecture of virtual switches were CPUs, where multi-table lookups were quite expensive. So, as a performance optimization, caching was introduced. Now, only the first packet visits the virtual switch pipeline, where its traversal is then used to generate a cache entry and installed in a Megaflow cache table. Subsequent packets perform a lookup in the Megaflow cache table and bypass the vSwitch pipeline. Because the CPU was the target, there was a need to design these caches while working around certain constraints. Caches had to be single table, so a Megaflow cache is a single table cache. And we had to rely on traffic locality alone for cache rule generation. But over the last decade, the underlying architecture for mapping the vSwitch has changed. Now, SmartNICs are the largest target architecture, which are pervasive in data centers, and they support multi-table programmable packet pipelines. But we have carried forward those assumptions about vSwitch performance optimizations that we made for CPUs. Therefore, we believe that it's high time to start with a clean slate for virtual switch design. So, how about we offload the whole vSwitch pipeline onto the SmartNIC tables? Well, it's infeasible. vSwitch pipelines support arbitrarily large packet processing pipelines and provide any size flow tables and any control flow abstractions to the control plane. SmartNICs, on the other hand, offer a handful of tables with restricted control flow. So we can't naively offload a vSwitch into SmartNIC tables and limit its flexibility. Therefore, we need to rethink caching, but instead of mapping a single large table, we've mapped traversals into multi-table pipelines of smaller tables. For this, we need to partition the original virtual switch pipeline into different sub-traversals. How does Gigaflow do it? Well, let's see Gigaflow in action. At time t equals 0, we have an incoming packet that misses the cache because all the tables are empty at the moment. We retrieve its traversal and partition it into 4 sub-traversals, and we convert them into cache entries and install the following. At time t equals 1, another packet arrives with different field values from the previous packet and finds no matching rules in the cache. It also generates a miss, and we get the following vSwitch traversal. This time we partition it as following and install 3 sub-traversal cache entries. At time t equals 2, a third packet arrives. If this packet were to miss the cache, then this is what the expected traversal in the vSwitch pipeline would look like. In fact, if we were still using a single table Megaflow cache, this would invoke a third miss and another lookup in the vSwitch pipeline. This is because single table caches capture traversals, and every unique traversal requires a vSwitch lookup and subsequent cache entry installation. But because we are working with multi-table caches and these entries set up in the SmartNIC, we're able to get a hit from the previously unseen packet. This is because these sub-traversals allow us to share cache entries across multiple flows and generate cache hits for unseen traversals. You can read more about the details in the paper about how we ensure correctness and also the sub-partitioning scheme. This multi-table pipeline in the SmartNIC that caches shared sub-traversals as cache entries is called Gigaflow. If we can identify the optimal set of such sub-traversals to cache, we can capture a powerful form of locality from the vSwitch pipeline that is called pipeline-aware locality. In leveraging this pipeline-aware locality, we see up to a 2 orders magnitude improvement in rule space coverage. We have implemented Gigaflow as a new caching subsystem in the widely adopted Open vSwitch, and the SmartNIC multi-table cache and OVS offload is implemented in the Xilinx Alveo U250 data center accelerator card using the P4 SCNet toolchain. The following is a demo of Gigaflow. We use Ansible for orchestration. In this demo, we have 3 machines: an orchestrator, a OVS-enabled machine, and a TGen machine, which sends traffic to the OVS machine. We now begin the experiment. Firstly, we install traffic into the TGen machine and pipelines into the OVS machine. We then start the OVS switch in the OVS machine, and then we install rules, pipeline rules, into the OVS machine. We also set up InfluxDB in order to be able to see real-time data and logs from the OVS. This is a Grafana dashboard which compares Megaflow and Gigaflow caches. So here we can see that Gigaflow immediately has a much higher hit rate than Megaflow. However, this gap only increases with time. We can also see the number of cache misses being way lower in Gigaflow, even though there's fewer entries in the cache. This is because the captured rule space is much greater in Gigaflow thanks to rule space reusability and sub-traversal sharing. We ran similar experiments with various different virtual switch pipelines. We compared the Gigaflow caches and the Megaflow caches, and we noticed that Gigaflow has massive improvements in several metrics. Gigaflow decreases the number of cache misses, increases the hit rate, increases the rule space reusability, decreases the number of cache entries required, and also decreases the forwarding latency. So to summarize, Gigaflow is a sub-traversal cache which captures pipeline-aware locality and delivers high rule-space coverage. All of the code is open source, and if you have any questions, please feel free to reach us at the contact information provided. Thank you for your time.